All right, so this is week 3. We're going to look at human factors and human performance improvement tools. These are going to be the methods or the various things that you undertake to perform any of these functions. So we talked about this a little bit, but with causation, so when we say X caused Y, what are we actually saying? Now, in the HPI realm specifically, or anything related to human error, cause will be confused with blame. Another thing to note is common sense, which is something you will run afoul of in most HPI investigations. That's not a real thing. There's no such thing as common sense. And if we're looking at, historical, we talked about this a little bit, but historical causation or traditional is, the focus is on the worker, not the organization, and machines are never at fault. But as you're looking into human error, human performance issues, you need to consider systems causation. So this is the idea that everything exists as a component of some system, and systems then are subcomponents of other systems, etc. So what are the characteristics of a system? You have a lot of factors and a lot of different variables, parameters changing constantly. Interdependency of components, that's a big one for us. And causal factors could be in many places or all of the places, possibly. In systems causation approaches, it's important to you fix the system rather than looking for blame. As investigators, you have to untangle the situation and find the root cause. The root cause, and we'll get into this a little bit more later, is the easiest way to understand it is the one cause that if it did not occur, the event or error or whatever is impossible to occur. And then when we're looking at corrective actions should repair the system flaws and design a solution which will prevent another occurrence. That is one of the struggles that we run into, is root cause is necessary for the accident, so therefore you have to solve the root cause. But a lot of corrective actions focus on the first half of that statement. They're trying to repair whatever the problem was, versus a thorough consideration of a design that wouldn't have that problem, wouldn't even the root cause. So it's almost, if we think of a root cause as what was necessary for the error to occur, you could redesign a solution or a system that root cause therefore is not possible. And that's kind of where, like I said, we're taking a different tack in this class where we're looking more at the design side of things. So here's some definitions. We'll get into this probably later in the course. We'll talk about some different accident investigation techniques and stuff. But just so you're aware, root cause, we already talked about that. A causal factor is a factor that shaped the outcome of the situation. Extent of condition is a specific term that's the extent to which that condition exists in other systems. Sometimes as you investigate a problem, you may be asked to perform what's called an extent of condition, where you're going to look at the entire organization or the entire system or things, and you're going to explore, hey, does this condition exist elsewhere? Barriers we've talked about, but it's a control to promote consistent performance and defend. Corrective actions are measures taken to correct issues of quality in the performance or the system, etc. An extent of cause, this is similar to extent of condition, but where else is the root cause present? This will be relevant, let's say you have an organizational failure or a cultural issue, then extent of cause becomes a big concern. So steps in an investigation process. We won't spend a ton of time on this, but this is, per OSHA, how you investigate a situation. When you take accident investigation, if you do that, we will go into this far deeper. So, you can pause the video if you want to take a peek at some of these, but otherwise we'll move past this because it's not as, I want you to be aware that these things exist, and that's kind of where, as you're going through investigations in the workplace or wherever, you need to be aware of the particular context or space that you're in. So this OSHA manual might be your guiding document, or if you're in nuclear power, for example, you might have a different one, or in firefighting, you might have a different one. So it's important to always make sure you're following whatever process is prescribed for your space. And while the OSHA one is a lot more detailed, this is the more basic one, right? You're going to secure a scene, document scene, do interviews, develop sequence of events, and then do your analysis, etc. This class, you could say, especially on the field investigation part, we're kind of looking at conduct interviews down. You may be involved in securing and documenting an accident scene, but not necessarily as immediate. And we just talked about this, but refer to your specific application spaces and adhere to the processes that are relevant for the situation and application space. The goal, ultimately, right, is to find the cause, not the blame. And these are just some phenomenal headlines. I love it. I love it when journalists get creative. So you tend to see some very funny capturing of what's actually occurring. So also we're going to talk a little bit about resilience and fragility. So obviously, right, we've covered aspects of this. When we talk about defense in depth, that's a measure to build resilience, and prevent fragility. So we really have to consider, right, what does resilience mean? And there actually is a whole field called resilience engineering, which specifically refers to resilience as essentially the ability of a system or personnel or whatever to cope with the unexpected. Now, when we talk about fragility, right, here's some different examples, and there's also one that's not in here that we'll talk about, but the Texas electrical grid. So, Texas has been having issues the last few years with their electrical grid. One of a personal anecdote I noticed, I was going to a conference in New York and had a connection at Dallas-Fort Worth Airport, and it was hotter in the airport than it was in the plane while we were sitting on the tarmac. And I remember I got a hold of one of my coworkers that works in the grid space, and he's also from Texas, and I said, hey, why is this airport not air conditioned? And he said, oh, it is, but I bet if they turn it on, it might trip the grid, because Texas's grid is currently very fragile. Similarly, California has these rolling blackout issues, right? That was a problem a few years back where PG&E was going to have to create rolling blackouts. This will be relevant for the firefighting aspect too, because the aging infrastructure, all the old power lines and stuff were fragile, and then their failures were causing wildfires. So PG&E was planning on, rebuilding that infrastructure, but it would take them years because they basically didn't maintain any of these lines for 10 years or whatever. So that's an example of a fragile system. Now that system, and similar with the Texas grid, though, we got to give them credit. The grid didn't have problems until weather events stopped making sense in Texas. But California's rolling blackouts that they were having in Northern Cal, that's designed fragility. And one thing I want you guys to consider, this isn't specifically relevant for this class, but as you're considering the systems, processes, organizations, whatever that you interact with on a daily basis, consider the drive to efficiency. So, and we're dealing with this in my work in nuclear power lately, where nuclear power is very expensive to just like run and operate and build. So there's pushes to increase efficiency. Well, efficiency and resilience are fundamentally opposed concepts. They are linked. Typically, like I have nuclear power safety systems here. Nuclear power safety systems are the definition of over-engineering, but they're incredibly resilient. They're also extraordinarily inefficient. So that's one of the things to consider, right? Redundancies are by definition inefficiencies because they are extra components or things you have to maintain and keep in place. And some may say, well, in the long term, that's efficient over 10, 20 years because, lost revenue if you go down, if a line goes down or whatever, is, greater than that. But let's say the lines never go down or anything, then it becomes efficiency. So that's a conditional efficiency, right? And the one that's not listed here is during the beginning of the pandemic, right? Everything went bonkers. Nobody could get anything. Partially, that was because of people overbuying, but there were massive supply chain disruptions. So, like I said, coming from the logistics space, there are few systems in the world more efficient than what was called just-in-time manufacturing. And that is how most of these supply or manufacturing lines around the world are managed and operated, is essentially they keep as much inventory of whatever X widgets in stock to maintain the line, but they expect that when they run out, essentially you put the last widget on while your coworker is unboxing the new box of one and putting them on the line. Like it's there's no wiggle room. And it's important to know most of the studies from the beginning of 2020, the supply chain disruption worldwide was on average like 12 hours. So consider that. A 12-hour, now given our lives were delayed for much more than 12 hours, but we're talking shipping vessels, trucking, all these things were delayed for about 12 hours on average worldwide. And we got supply chain shocks that we're still seeing 4 years later. So it's important to note that, right? When you're dealing with a system that is incredibly efficient, it's also probably pretty fragile. And that's one of those things to kind of consider. And we've talked about this, kind of beat it to death, sources of human error. But I wanted to know, I found this slide and I realized but I might have talked about this in the first week, but I don't recall, and I don't think I had these images. So these are example images of kind of the birth of human factors in World War II, where pilots were crashing their planes and nobody could figure out why. These were well-trained pilots and everything, and come to find out the lever for the landing gear and the lever to drop their flaps were right next to each other underneath the seat, so they were not visible to pilots in the cockpit. So they would reach down and consistently pull the wrong one. So they would pull the wing flaps down, which would force them to drop, and they didn't have their landing gear out, so they would crash on the runway. And the solution was, let's make the levers shaped like a wheel and a wing flap. And suddenly overnight, people stopped having problems. So that was kind of the birth of it all. And, that's an ergonomic adjustment is what we would call that in human factor space. It's not a cognitive shift, but, it's important to consider, right? Simple mistakes. These people, they really scratch their head over why these pilots were wrecking planes when they were super well trained and all these things. And that wasn't consistent either, because sometimes they would grab the right lever. You wouldn't know until you really do structured user interviews. And that's kind of an aspect of one of the comments in the Slack was about whether the manufacturers of that system would have considered that somebody could enter commands quickly. And that's another saying we say in human factors, that no design survives contact with the user. So a user will fail or succeed in ways the designer never intended. And so that's one of the things we stress in our work, is to bring us in as soon as possible, so that when we come in and either between our expert reviews or user reviews, we give some significant changes to the developers. You want to make sure that you're not stuck in you've over invested in the system as it sits before you even explore it with users. Literally, the time to first describe your system or interact with users should be before a system is even in existence, before a single line of code is written or a single prototype is built, because we just don't know how they're going to use it or not. And you won't know that, so you wouldn't know that the nurse would enter the improper commands so quickly, because you never looked. You never tried to see how that would be used in the wild. Now, we talked a little bit about these with human error, but these are just some of the big human biases and heuristics. So Judgment Under Uncertainty is the paper. If you are interested in this, I strongly recommend you pick up Thinking Fast and Slow by Daniel Kahneman. It has the Judgment Under Uncertainty paper in there, as well as a bunch of other aspects of human error, and specifically our biases and heuristics. He did most of his work with Amos Tversky, who passed away before they won the Nobel Prize for their work, which is unfortunate. But very interesting. Thinking Fast and Slow is really, really interesting, and it's very good treatment of cognitive psychology and performance. But these are the more common ones you're going to run into. And keep in mind, these are not theories. These have been proven 6 ways to Sunday. This is what people do. So when you're thinking about human performance, your operators or whoever will have done these things in this instance, regardless of what happened. So satisficing is your best available, not optimal. So our brains will typically jump to a satisfactory approach, but not the optimal approach. And this is something that will always happen. Stress increases the likelihood of this. It's something we call premature closure, where they just pick the first functional strategy that they think will work. They don't consider beyond that. So that is one thing that can sometimes be the source of your error. Now, recognition heuristics, recognized alternatives are more valuable in memory. So they are, paths that your agent has taken and is aware of and recognizes will always be more likely to be selected than others. Similarly, it's linked with availability. Quick retrieval of an option makes it more valuable. So when we think about the availability heuristic, that is typically a recency. So the most frequently used memory schema process that we undertake, procedure, is the one that your brain's going to serve to you. Representativeness, or the representative heuristic, if X is similar to Y, then it's in the same category as Y. That isn't true logically at all, but that's how our brains think. Anchoring and adjustment. So arbitrary numbers can affect true numerical judgments. This is there's a series of really interesting studies, even ones including how bad so humans typically are not very good at understanding statistics. Even, and they actually cover this in Kahneman and Tversky's work, even trained graduate level statisticians frequently misjudge statistics and make poor choices. So anchoring and adjustment is a specific one where you say choose a number and they anchor their judgments around a certain specific number. Or you say, you know, let's say it's a good example is like a Price is Right scenario. So, you know, hey, how much is this, you know, laundry detergent? And maybe you have a memory of purchasing laundry detergent once and it was $12 or whatever. Without consciously thinking about it, any of your guesses will be anchored to that $12 value. And that is a problem. And then there's, if you Google it, there's tons of other examples. We won't spend a ton of time on it, but you have to keep in mind your brain does weird things specifically around numbers. And anchoring can be a really big problem, especially when we're talking about systems or processes that have very delicate situations surrounding numbers, things that maybe run off of temperatures and, you know, more complex systems. So yeah, we just talked a little bit about this, what we're good and bad at. So we're intuitive grammarians, but not statisticians. Like I said, you'll find that in the Kahneman Tversky work. That means that we're very, very good with language. You know, how many times have you been talking to somebody? I know I deal with this with my kids constantly, and they're trying to tell me something that makes absolutely no sense on the face. But because of contextual clues, body language, different aspects around it, we can understand each other. You know, we're much better at that than we are at understanding math and numbers. The Dunning-Kruger effect. So this is, you know, this is an election year, so you're going to get this thrown around a lot probably. But the basic principle is we're bad at self-judgment in the sense of we overestimate everything that we can do. We think we're smarter than we actually are. We think we're better at something than we actually are, etc. You know, and that's one of the big aspects that underlies a lot of, you know, online interactions, I would say. Future consequences, we're really bad at that. We discount negative consequences and we overestimate positives. That's why people play the lottery. Vigilance, we talked about this before, you know, continual attention is one of the most difficult things for the brain to do. That came from William James' work in the early 1900s. And repeated, precise tasks. That is not something we are good at. That's something machines are great at, though. Now, we're going to go into the human factors tools a little bit, but, you know, and then we'll pivot harder to HPI stuff. But, again, we're thinking about how a system comes to be and the aspects that maybe are considered or should be considered in its creation that maybe led to poor performance at the end of the road. Now, these are just some examples, and these are really formalized examples that that don't map to most instances, but they are structured tools that we use in human factors, and in particular, any kind of complex systems engineering. And we'll notice this, right? User experience, which is the kind of human factors for software, and other kind of disciplines make use of these. Just maybe they call them something different or they're not as rigorous. But let's start with task analysis. So task analysis is a structured evaluation of a task. And the question, right, is did we set up the user for success? We use task analysis to determine how you perform a task. What does a success look like? What are the feedbacks that are involved? And what factors influence your performance? There's pros and cons. obviously, with everything. But when do you use task analysis? When task construction is critical to success and you're not totally sure where your error points live. Like, you know there's error likely situations, but you're not sure what step is the problem. You also use it to break a task into subtasks. You can identify what should have happened, because right, if you perform a task analysis, you will end up with the optimal or best example of a task. And it's used to identify deficiencies in training, procedures, and procedure adherence. And one of the things I want also to know on procedures, because I know where Drew will be, he has a lot of experience with procedures, but in the firefighting realm, that you're doing, Maddie, it's a little bit different. You don't have paper procedures in the way that like nuclear operations does. But keep in mind, all of the processes that you still undergo have a procedure. You might adhere to them differently than reading a piece of paper and checking off boxes. Now, advantages of task analysis is it familiarizes you with the task. Obviously, right, this is something when we get into interview techniques, when you ask somebody that something went wrong, right? Oh, well, what were you supposed to do? What was the correct series of events? What you're essentially doing is trying to identify that optimal path. It does help to identify where problems occurred while performing the task, and it can inform many different mitigations or corrective actions. Now, limitations. Task analysis is time consuming. Walkthrough task analysis is the most effective, but it's only if performed with personnel normally responsible for the task, which may be difficult to arrange. It can be difficult to complete without first-hand experience, obviously, unless you're doing it with a guide, someone who actually does it. And you can lose the forest for the trees, because if you remember system causation, task analysis is the reverse. We're not looking at a system, we're looking at individual tasks as a component. And that's one of the critical aspects to realize. Steps in a task analysis. So first, you define the scope of the task analysis. So what tasks, conditions, procedures, what are you looking at? Collect the data through observations, interviews, talkthroughs or walkthroughs. You interpret the collected data. There's a few different methods for this. Hierarchies, lists, tables, etc. And then you identify error or failure points, training failures, procedure issues, etc. Especially with expert populations, what you'll find is many of them have found workarounds of error points. Maybe they made this mistake once and then they adjusted their behavior. But it doesn't, it's what we call tribal knowledge. It's in their head, but it's not written anywhere or anything. So how do you communicate that to other users? So we'll go through this kind of quick. Again, you don't need to know this stuff specific, like in intense detail. If this really scratches an itch you have, let me know, and we can go into it maybe if we have some time at the end of the course. But you're going to interpret the collective data. So how do you represent the information? These are the four main ways you do it: hierarchical, tabular, link, or applied cognitive task analysis processes. And we'll go through each real quick. So hierarchical task analysis, there's a top-down method. You begin with a goal, and then you break it down into the subtasks. Depth can vary, and it's not going to capture communication or extra task issues. Extra task means external to the task, like extraneous. So things that are surrounding it, you're not going to catch those with task analysis typically. Next, tabular task analysis. This is a bottom-up method. You begin with a subtask function, build the action levels up. It's incredibly detailed and time-consuming, but you do capture cognitive steps and decision-making well, and it captures task support and communication well. Link analysis. This is kind of a meta approach, really. It's intermediary, so you live between your tasks. You're focused on the links between tasks. This is, we might consider this as like you're trying to find transition points of concern. So communication steps are going to be caught, any kind of process or system interactions, and it's useful for teaming or handoff situations. Then applied cognitive task analysis. So this is, it depends. This is the more psychologically valid one, and one that you'll see across psychological studies, but it's focused on the cognitive demands of a task. So it's going to capture the information needs, cognitive demands and error traps become apparent, and cognitive supports like decision aids will be captured. And I'm actually going to end this one here, but starting next week, I'll finish these slides and we'll go through function analysis and allocation. So functional requirements analysis and allocation, we're essentially deciding what needs to be done and who is going to be doing it, the human or the system. And we will go through that next time. Thanks.